480。
打ち上げ8分前です。現在、各系ともロケット打ち上げの最終作業を行っています。また、警戒区域の安全は確認されています。
It's 8 minutes to the launch. All systems are now in final operations. The restricted area has been vacated.
460、59、58、57、56、55、54、53、52、51、450。440。430、29、28、27、26、25、24、23、22、21、420、19、18、17、16、15、
安全系準備完了。
13、
The
12、
safety system is go.
410、409、408、407、406、
車両系準備完了。
404、
The range
403、
system is
402、
go.
401、400。390。380。370。360。
打ち上げ6分前です。現在、車上の天候は晴れ、気温摂氏 28.6 度、北の風毎秒 5.5 メートルです。H2A ロケット47号機の打ち上げに問題はありません。
It's 6 minutes to launch. The current weather at the launch site is fine. Temperature is 28.6 degrees Celsius, and wind is 5.5 meters per second from the north. The weather has no constraint for the launch.
本日の打ち上げ予定時刻は日本時間の午前8時42分11秒です。
Today's scheduled liftoff time is 8:42 and 11 seconds a.m. Japan Standard Time.
310、309、308、307、306、305、304、303、
衛星系準備完了。
301、300。
The satellite system is go.
290、89、88、87、86、85、84、83、82、81、280、79、78、77、76、75、74、73、72、71、270、69、68、67、66、65、64、63、62、
現在ロケットの管制は吉信発射管制塔から行われています。
The H2A launch vehicle is now operated under the command of Yoshinobu Blockhouse.
250、49、48、47、46、45、44、43、42、41、240、39、38、37、36、35、34、33、32、31、230。220。210。200。190、89、 88、87、86、85、84、83、82、81、180。
打ち上げ3分前です。
It's 3 minutes to the launch.
全システムの電源が外部から内部に切り替えられました。
170。
The power has been switched to the internal systems.
1段液体水素系準備完了。
The first liquid hydrogen system has been pressurized.
150。140、39、38、37、36、35、34、33、32、31、130、29、28、27、26、25、24、23、22、21、120、19、18、17、16、15、14、13、12、11、110、109、108、107、106、105、104、103、102、101、100、99、98、97、96、95、94、93、92、91、90、89、88、87、86、85、84、
2段液体酸素系液体水素系準備完了。
The second stage liquid oxygen and hydrogen system has been pressurized.
74、73、
1段液体水素系準備完了。
69、68、67、66、65、64、63、62、61、60、59、58、57、56、55、
The cooling water system for the flame deflector has been activated.
50、49、48、47、46、45、44、43、42、41、40、39、38、37、36、35、34、33、
ウォーターカーテン散水開始。
31、
The sound suppression water system has been activated.
27、26、25、24、23、22、21、20、19、18、17、16、15、14、13、12、
フライトモードオン。
10、
The flight mode is on.
同様電池起動。
The thermal battery has been activated.
全システム準備完了。
All systems are go.
メインエンジンスタート。
The main engine ignition.
XRBA 点火。リフトオフ。
Solid boosters ignited. Lift off.
プリズムスリムを搭載した H2A ロケット47号機は2023年9月7日午前8時42分11秒に種子島宇宙センターから打ち上げられました。
We have a liftoff of the H2A launch vehicle number 47 from JAXA Tanegashima Space Center at 8:42 and 11 seconds a.m. on September 7th Japan Standard Time.
打ち上げ以降ロケットの管制は吉信発射管制塔から竹崎総合司令塔に引き継がれています。
Following the liftoff, the operation control of the H2A has been switched from Yoshinobu Blockhouse to Takesaki Range Control Center.
60、
打ち上げ後1分が経過しました。
It's 1 minute into the flight.
70、
ロケットは現在東方向の太平洋上へ飛行しています。
The H2A is now flying above the Pacific Ocean to the east.
83、84、85、86、87、88、89、90。
XRBA 燃焼終了。
Solid boosters have burned out.
100、
110、
SRBA 分離。
12、
Solid boosters
13
have been
14、
separated.
15、16、17、18、19、120。
小笠原局でのロケット追尾が開始されました。
Ogasawara Station has started tracking the H2A.
第1段エンジンの燃焼は正常、制御系、飛行経路も正常。ロケットは順調に飛行を続けています。
The combustion of the first stage engine, Archer control, and the trajectory are all nominal. The H2A flight is on course.
現在のロケットの高度は約 48km、148km、秒速約 1.9km です。
Current altitude of the H2A is about 148 km.
上部衛星フェアリング分離。
The upper payload fairing has been jettisoned.
打ち上げ後5分が経過しました。
It's 5 minutes into the flight.
第1段エンジン燃焼停止。
The first stage engine cut off.
第1弾、第2弾分離。
The first and the second stages have been separated.
第2弾エンジン第1回燃焼開始。
The second stage engine ignition for the first time.
「打ち上げ後9分が経過しました」。
It's 9 minutes into the flight.
「打ち上げ後10分が経過しました」。
It's 10 minutes into the flight.
第2弾エンジンの燃焼は正常、制御系飛行経路も正常、ロケットは順調に飛行を続けています。
The combustion of the second stage engine, true control, and the trajectory are all nominal. The H2A flight is on course.
現在のロケットの高度は約 552km、秒速約 6.0km です。
Current altitude of the H2A is about 552 52 km and velocity is about 6.0 km per second.
第2段エンジン第1回燃焼停止。
The second stage engine cut off for the first time.
XRISM 分離。
XRISM separation.
XRISM の軌道への投入を確認しました。
XRISM has been inserted into the orbit.
ロケットはこのまま完成飛行を続け、まもなく小笠原局の受信範囲を離れます。
The H2A is in a coastal state now, and shortly it will proceed beyond the tracking area of Ogasawara Station.
次のイベントまで一旦実況放送を中断いたします。打ち上げから約47分後にスリム分離を予定しています。
The separation of SLIM will occur in about 47 minutes into the launch. Until the next major event, there will be an intermission.
竹崎総合司令塔からの実況放送は午前9時25分頃に再開を予定しております。
This live coverage will resume at about 9:25 a.m. Japan Standard Time.
We are watching the live coverage of the launch sequence. XRISM is separated. We have received message videos, so please take a look at them.
I'm Richard Kelly from NASA's Goddard Space Flight Center, and I am very happy that we are finally on our way into space to begin a new journey with the X-ray imaging spectroscopy mission. I want to congratulate JAXA and the rocket team at Mitsubishi Heavy Industries for getting us this far. This took an enormous amount of work, and my colleagues at NASA are extremely grateful and wish to congratulate them on their success. Astronomers from around the world have eagerly anticipated the launch of XRISM and the new capabilities it will provide for high-resolution spectroscopy and wide-field imaging. We are now a major step closer to exploring the universe in X-ray light with a powerful new tool to reveal what is going on in so many celestial objects in our galaxy and all the way out to distant clusters of galaxies that are emitting X-rays due to their extreme temperatures and energetic conditions. We will soon bring this new observatory online and get to work. So congratulations and go XRISM team.
XRISM プロジェクト
I am Tashio, principal investigator of the XRISM project. Tenma in the 1980s, ASCA in the 1990s, and Astro H in the 2010s. With their then state-of-the-art spectrometers, Japan always led the world in X-ray astronomy. This time again, the world's best spectrometer will be launched into the space. We are determined to use XRISM to capture the world's best spectrums to lead the world in X-ray astronomy. Please continue to support our mission.
The first video was by Dr. Richard Kelly of NASA, and the second was Professor Tashiro, principal investigator. Now we will be discussing XRISM in more detail. From XRISM project scientist Professor Matsushita, and from science operation team Dr. Shidatsu are with us. And about XRISM science research, I would like to ask of them. First, Professor Matsushita. Yes, I was watching anxiously, but successfully XRISM was separated to my great relief. Over the next 3 months, carefully, validation systems will be deployed, and so we will have to continue to be watching carefully. But first step was successfully done. 3 months after, scientific observation will be carried out, and we would like to be able to report the first light. About XRISM satellite, I would like to explain. Can I have a slide? And Dr. Shidatsu, please explain about the XRISM and detector. I would like to explain. Can you see the slide? Is the slide being shared? XRISM length is 8 meters, about 3 stories high, and 2.3 tons is the mass, and width is 9 meters when solar panel is deployed. Height is 550 kilometers, and it's at inclination of 31 degrees, and period is 96 minutes. From the space, X-ray arrives to the left top part of the satellite and will come into the satellite. In this cylinder, there is X-ray telescope. Using X-ray telescope, X-ray will be gathered. The focus of the telescope, the right bottom area, have 2 detectors. First is X-ray microcalorimeter Resolve. Resolve uses freezing systems, including liquid helium, and cooled to negative 273.1 degrees. And at super high resolution, X-ray will be observed. Next is X-ray CCD camera Extend. In comparison to Resolve, Extend has wider angle and will be able to observe an area of a sky equivalent to a full moon at a time. Using these 2 equipments, observation will be carried out.
So, from my side, the scientific research plan of XRISM. Dr. Shidatsu will give the latter part of the explanation. Then if you go to the website, you can see how to see the cosmic winds. How should I give the explanation on this? This is the topic I would like to talk about. As has been already explained, the telescope and detectors are on board. And what is X-rays? This is the starting point. X-rays are part of the electronic magnetic waves, like the ultraviolet as well as the lights. They are part of the electromagnetic waves with the high energy, with the short waves. X-rays cannot penetrate the atmosphere, and so the satellite is essential for the observation. As has been already explained, 1 million degrees and the 100 million degrees, the objects will be able to be observed by this X-ray astronomy. There are 2 detectors on board. The first one is resolved. This means the resolution and also determination. So these 2 things are contained in this term. Now let us compare the performance. As you can see, this is about the Astro H observation results. perceives the clusters of a galaxy, X-ray spectroscopy, and you can see the colors in the X and Y axis. You can see those are the two detectors that are going to onboard and similar to the ones that we have. The black represents the Astro H microcalorimeter, and the red one is a Suzaku CCD. The microcalorimeter, if it is going to be used, X-ray color, that is the axis you will be able to see how accurate it is. And similar to the sound, when it comes to the light, it is affected by the Doppler effect. If it is approaching, and then the blue shift, and then if it is going distant, red shift. And this is going to be applied to the observation. X-ray color can be observed accurately, and you will be able to see the sources, or like the high temperature gas, and can be analyzed accurately. And on top of that, you can see chromium and manganese. Those rare elements, they are going to be X-rays emissions, as you can see in the chart. Those small, the minor, the X-rays can be detected for observation. And then X-ray space-based space. How is it going to be observed? When it comes to the Milky Way, you can see the near-infrared observation on the top. You can see the disk that spreads around. We are within this disk. And then X-ray has observed this galaxy on the bottom, in the bottom. You can see a different view. X-rays will use the emitted by the gases with high temperatures. In the case of the Milky Galaxy, you can see millions of degrees of X-rays can be observed. You can see the speed of the cosmic wind, and there are different the celestial objects. They are called supernova remnants. Those two remnants, the left one is about 300 years ago. It is the remnant of the supernova explosion, and it's 16 light years wide. And on the right-hand side, 11,000 years ago, there was the explosion, and 250 light years expanse. So you can see the effect of the explosion. XRISM will be able to observe the X-rays emitted from those supernovas, and then we will be able to observe the elements and the speed of the gases. In fact, around ourselves, when it comes into those elements, they are produced in the supernovas. And as you can see, we will be able to analyze the alchemy of the space and the speed of the wind and the evolution of the galaxies. We will be able to detect them. And you can see this round object. These are the clusters of galaxies. Hundreds of galaxies are going to be combined together. And you can see this is the enlarged picture, X-ray picture, which is enlarged, and about 600 billion years away, with the expanse of several light years. And they are trapped in the high temperature gas in the core. And most of the elements in the space are produced and then exist in the form of a high temperature gas. XRISM will be able to detect these objects, and then how those objects are growing in the space-time. They will be able to be observed. And there's some percentage of the elements that were produced in supernova are spreading around, and we will be able to observe them. In the core of this stellar object, this is M87. And this M87, this X-ray picture can be captured on the left-hand side. From the galaxy, there is a high temperature gas is emitting. And on the right-hand side, this is the microcalorimeter, which captures the spectra, which is expected to be captured. the pinkish, the dotted line represents the Suzaku results. And you can see different kinds of information and data can be captured. A XRISM, a satellite, will be able to observe the emissions of those gases from AM87. Then, how's the wind blows from this place?
Yes, thank you. Shiratsu speaking. M87 was just mentioned. In the center of the image of the galaxy in a white square, that is the center of the galaxy. In X-ray, we can see that it is very bright. And if this is enlarged further, it is about 6.5 billion solar mass. There is a supermassive black hole. It is known to exist. And such supermassive black hole is estimated to be at the center of each galaxy. Other than supermassive black holes in the universe, there are various black holes, including small and large ones. For example, at the right side, this is a different galaxy, and visible light and X-ray are superimposed. And looking at this, other than at the center of the galaxy, there are some bright spots under X-ray. And this is also a black hole, and these are paired black holes. And these are several tens of times larger than solar mass, stellar mass black hole. And these are circling each other in a very short distance. They are attracted by the strong gravity of the black hole, and they are falling into black hole as they encircle, creating a disk at the center. And the gas temperature is as high as 10 million degrees, emitting very strong X-ray, and that X-ray is observable in the image above. There are small and large black holes. They not only absorb things, but as Professor Matsushita mentioned earlier, high-speed gas is emitted. For example, on the left side, this is a jet, and light velocity is 300,000 kilometers per second. The speed is as fast as that, and the falling disk above that, there is a wind emitted, as shown on the right side. The velocity of the wind is several hundreds of kilometers to 10,000 kilometers per second. Earlier, rocket, when XRISM was separated, it was traveling at about 8 kilometers per second. In comparison, the speed is much, much faster. And in a supermassive black hole, these jet or wind are emitted, and surrounding stars and gas may be moved and affect the formation of the galaxy itself. That is the estimate. But why do jet and wind come from the black holes? And to what extent do they affect the surrounding environment? That is not fully elucidated. With XRISM, we hope to be able to understand this mechanism. For example, as shown at left below, around the black hole, there is a wind, and let's say we observe this wind near the black hole. There are various types of X-rays with different levels of energy. And X-ray, the gas coming out, if we observe the wind, we can look at the element such as iron that will be absorbing a certain level of energy. And as shown on the right side, we can see a spectrum of absorbed energy. The wind is moving, and due to Doppler effect, from the original energy level, absorbed energy is observed at a little different time difference. And with that, we hope to be able to estimate the level of energy. And the black line showing absorbed energy, we were able to have very rough idea, but with the resolve on XRISM, each line of absorbed energy can be understood more precisely to understand the intensity and absorption of energy, how much gas at what velocity are emitted to the surrounding environment, and how much it is affecting the environment. We hope to understand that better. And with X-ray observation, time-space distortion may be understood. That is also hoped. Near the black hole, because of theory of relativity of Einstein, there is a distortion of time-space, and EM wave that is emitted will be observed with a distortion. The right side diagram shows the iron light line emitted from the black hole, and there are several peaks spread over widely. And this spread shows the distortion of the timeline. By understanding the shape of the emission line, we should be able to understand the degree of distortion of time-space around black hole. And black hole rotation, the faster the rotation, the effect is larger, and the range will be spread wider. So by understanding this, we should be able to measure the speed of the rotation of the black hole. Not only near the black hole, but at a distance from black hole, there may be a gas and wind that are absorbed. Then smaller emission lines and absorption lines will be mixed. With the existing equipment, it was difficult to distinguish, but with resolve, as shown in red line, various different components can be separated to understand the distortion of time-space around the black hole in more precise way. That is the hope, and in this way, so this is only a part of what we are hoping to achieve with XRISM. We would like to understand the mystery, unravel the mystery of universe using XRISM.
Thank you very much. And having listened to your presentations, XRISM has a very fancy name given to. The resolve means the dissolution, and then resolve also means determination and fortitude, and then extend. This represents extension of the idea, so to speak. Similar to XRISM, well, as captured in XRISM, how do you come up with a specific naming? Microcalorimeter, Rich Kelly, Mr. Calorimeter, AK, who has named this machine with the instrument in that way. Thank you very much. And the viewers probably are most interested in this topic, the distortion of space-time and black holes. And it is going to go up into 10 million degrees. And I am a scientist on the solar system, and then the temperature is like 1 million degrees, but it goes up into 10 million degrees. The flare is supposed to be the reason for this kind of creation. But in terms of the theory, do you have any specific ideas? When it comes to the black hole, the temperature surrounding it, the gas comes down, declines, and it resolves and rotates at a huge speed. And then, as a result, the temperature goes up to 10 million degrees. So there is this theory, but theory is going to be corroborated and by the specific observations and by the result or the XRISM. And that's the process and that the scientific mission is going to be made as for XRISM. Thank you very much and for your talk. Next, Slim.
I would like to introduce Slim to you, and we have a video message from the project manager. So please take a look together with the video introduction of the project. Hello to everyone watching this live streaming event. I am Shinichiro Sakai, project manager of SLIM, Small Lander for Investigating Moon. I think you're all watching the live streaming with much excitement, waiting for the launch of SLIM. I feel the same. It has been 7 years since the start of the project. If you go back to when the idea was originally conceived, it has been more than 20 years. With the support of many and efforts of all those involved, we are now welcoming the day of the launch. We have dedicated so much efforts and great deal of thinking in SLIM, with which we aim to achieve lunar landing with unprecedented precision, to open the door to the next generation of lunar exploration. We are determined to stay focused even after the launch. From the era of landing where we can to landing where we want. Please continue to support us. From Professor Sakai, project manager, we have heard a very strong message. And we have Professor Mori, who is a member of SLIM project, and Professor Otake, payload manager. We are still watching the launch sequence, but how do you feel? Project manager Dr. Sakai said that from the era of landing where we can to landing where we want, that comment was mentioned. I think this is a symbolic phrase of the landing by the SLIM. Lunar exploration in the future will lead to leading-edge observation, and for long-term sustained observation, precise pinpoint landing is essential. And SLIM will be taking on the challenge of precise pinpoint landing to open a new era. Thank you. Pinpoint landing was mentioned, and we will come back to this point later for more detail from Professor Mori. But Professor Otake, would you like to comment? Yes. Watching Sakai-san's video once again, and watching after the SLIM video, I'm also feeling the renewal of my determination, and I also feel a great deal of excitement. And as Professor Mori mentioned, pinpoint landing from scientific viewpoint is very important. Where in the moon, what geology exists. To an extent, we understand that, and we therefore have a place in mind where we would like to conduct the research. And in a targeted location, to achieve landing is very important. Researchers are hoping to land on some precise point, and that is known because of the past missions. You know the distribution of substance in certain areas. So in the next mission, there's a more precise targeted location for landing that is being aimed at by this project. So we would like to ask more about that later.
Now, there are some questions about SLIM. We have received them. On the back, you can see the model. Let us use this model to ask questions. The one thing I would like to ask of you is that this body on the left-hand side, this triangle, cone-shaped silver dent, what is it? This is antenna, S-band antenna. There are several of them, as a matter of fact. And so at whatever directions, the vehicle will be able to be engaged in communication, and thrusters as well, which are attached. And I will come back to this point later on. So on the back, on the right-hand side, so the small-sized components are gas thrusters. The brown one is the main engine, and smaller ones are 22 Newton small-sized thrusters. So they are going to be combined together for landing operation. Thank you very much. And that is the answer. This is the S-band antenna for telecommunication. Thank you very much.
We have another question. Maybe I should ask this of Professor Otake. Do you yourself would like to land on the moon? And if so, what would you like to do on the moon? Yes, I would very much like to visit moon. That is the place that I would like to visit the most. And if I'm on the moon, because I study rocks, as I mentioned earlier, I would like to bring back rocks to analyze further. There are many rocks I would like to bring back. So I would like to collect rocks more than I can carry and analyze them as much as possible. Moon scientist, I would like to go to the moon, but as a solar scientist, if I visit the sun, I will be burned. It's difficult to visit the sun.
I think the separation of a SLIM is going to take place soon. So we will switch the camera to Tanegashima Space Station.
種子島宇宙センター竹崎総合司令塔から H2A ロケット47号機の打ち上げ実況放送を再開します。
This is a live coverage of the H2A launch vehicle number 47 from Takesaki Range Control Center at JAXA Tanegashima Space Center.
ロケットの追尾は再開されており、現在ロケットは完成飛行を続けています。
We have restarted tracking the H2A. The launch vehicle is currently in a coastal state.
下部衛星フェアリングが分離していることを確認しました。
We confirmed that the lower payload fairing has been jettisoned.
第2段エンジン第2回燃焼開始。
The second stage engine ignition for the second time.
第2段エンジン第2回燃焼停止。
The second stage engine cut off for the second time. Separation.
SLIM の軌道への投入を確認しました。
SLIM has been inserted into the orbit.
これをもちまして H2A ロケット47号機によるXRISMおよびSLIMの打ち上げ実況放送を終了いたします。
We will now conclude our live coverage of the H2A launch vehicle number 47 with on boards XRISM and SLIM.
はい、ご覧いただきました
As
通
you
り、
have
小型
watched,
非着陸実証機
SLIM
スリムは
smart
予定
lander
された
for
軌道に向けて
investigating
分離されま
Moon
し
is
た。
separated to move
話
onto
も
the
ありまし
planned
たけれど
orbit.
も、まずは一
As
安
you
心という
saw
ところですか
the
ね。
applause,
はい、
I
で
think
は、
we
引き
are,
続きスタジオではスリ
I
ムについ
think,
てお話を伺い
relieved
ます。
by
でま
the
ず
fact.
森先生からですかね。
And
よろしく
first,
お願いします。
Dr. Mori, over to you.
スライド切り替わりますでしょうか。
Can you show the slides? Not these slides.
はい、それでは、スリムについて
So about SLIM, I would like to introduce SLIM. The mission of SLIM are twofold. First, as shown here, achieve a pinpoint landing on the moon to demonstrate that technology, and that is landing where we want to land. And the precision of landing on the moon was within the range of few kilometers to 10 kilometers, but we would like to make that more precise to about within the range of 100 meters. The key technologies are image-based navigation and navigation guidance and control. As for vision-based navigation, you may know of this from Hayabusa 2. Astronomical bodies will be captured in images, and based on the characteristic features such as rocks, the spacecraft will know its own position, and this is applied for the first time for the moon. What is different from Hayabusa 2 is that SLIM also has autonomous navigation guidance and control function. Hayabusa 2 was landing on an asteroid with a microgravity and was able to approach asteroid slowly. However, in case of SLIM, Hayabusa 2 was able to approach slowly, and operators manually were able to check the photographs and give command to Hayabusa 2. But in case of SLIM, gravity is larger, significant on the moon, and it will be falling very fast. So SLIM cannot wait for the command and will have to make its own decision. That is the major difference. Another difference is because of a significant gravity. In case of the moon, once descent starts, there is no redoing. In case of Hayabusa 2, several attempts were possible. After rehearsals, the landing took place, but this time there is only one opportunity. That is also a major difference. And the second objective is demonstration of a lightweight lunar explorer computation system for chemical propulsion, or rather chemical propulsion system and computation system will be tested. These will be made as lightweight as possible so we can carry more payload. Please take a look at the video of the SLIM mission.
So
there was an applause earlier after the successful separation of the SLIM, and SLIM itself will be flying. It will use Earth swing-by and lunar swing-by, and tidal force of the sun will be used to save fuel to arrive at lunar orbit. And as I mentioned before, vision-based navigation with a camera will be used to detect a crater to know its own position, and thruster will be used to lower the altitude. And this is motion descent, powered descent. And then attitude will be upright to vertical position. Landing radar will be used for safe landing. At 50 meters altitude, photographs will be taken to detect obstacles and search a safe area to land autonomously. And it will be moving to a safe landing position autonomously. Right before landing, small probes will be released. And SLIM itself will be landing in two-step way. In this way, it will land. And we hope to be able to see this. Photographs will be captured by what we call Lev 1. It not only will take photographs, it will be hopping, so that experiment is planned. There is another one, Lev 2. This is the size of baseball, and it will change its form, shift its form to move about the surface of the moon. And the SLIM will also be conducting optical observation. Why do we have to have pinpoint landing? In the past, on the surface of the moon, many landers have landed, including by the former Soviet Union, the United States, China, and India just a couple of weeks ago succeeded in landing. In case of the former Soviet Union, 2 weeks ago they attempted, but were not successful in landing. And in these landing, wide safe area, large sea is selected for landing. So landing precision can be within the range of few kilometers to several tens of kilometers. But Kaguya made a difference. Kaguya was launched in 2007 on a lunar orbit, and NASA launched Lunar Reconnaissance Orbiter. High-resolution lunar observation data is now available in large volume, and now there is a need to do a research of a certain rock near a certain crater in lunar exploration. This requires precision of about 100 meters in landing. About a SLIM lander, this is the overview. First, the weight is very light, 700 kilograms. This is about as heavy as a light vehicle. 3/4 is propellant. Excluding propellant, it is 200 kilograms, very light. And salient feature is the tank. Usually we have separate tanks for fuel and oxidizer, but this is an integrated tank for the fuel and oxidizer. And this is also the main main body, or various things are attached, including thin film, solar panel, and camera, main engine, and thrusters are attached to the tank. That is the structure of the SLIM. This is the trajectory of SLIM. As much as possible, fuel consumption will be minimized. So solar swing by, Earth swing by, and lunar swing by will be used. Also, solar tidal force will be used. Towards the end of the year, we expect the spacecraft to be on the lunar orbit and eventually land. This is the landing sequence. From 15 kilometers of altitude, motion powered descent will start. And with autonomous navigation, guidance, and control to targeted location, lander will approach. And at altitude of 7 kilometers, it will upright to vertical position and will also conduct observation. And at 50 meters altitude, it will detect obstacles and will eventually land. And this descent phase is about 20 minutes. This is 20 minutes of terror. We believe we will be very nervously watching this 20-minute landing phase. The landing area is a slope. And so rather than landing on the landing gear, it will be a two-stage landing to change the attitude from upright to horizontal. So I would like to show you how this will be done. You have something mysterious in front of you. This is the mock-up of a SLIM, model of SLIM. This is a slope. This is a representation of a sloped lunar surface, and it will land in this way. It's actually two-step. Main gear will land, and after that, the front gear will land to take horizontal orientation for safe landing. pinpoint landing on a targeted location. In addition, it will be landing on a slope. And as inclusive of that, we would like to achieve landing where we want to land. Thank you.
So given the name slim, a narrow shape can be considered. But when it comes to the attitude for landing, it is supposed to be a boxy style and lightweight. And then it is going to be, each gear is going to be used for the smooth landing. Right. That is the landing operation. So it is completely different from the conventional landers. The size-wise, it is much smaller. So if you take a look at all the details, it betrays the conventional wisdom. So it is going to land where we want to land. And that is supposed to be the prerequisite, the requirement. And then I would like to hand over the microphone to Dr. Otake for the reason why we are going to land that specific place. Now, I would like to talk about the scientific purposes. The moon itself, it was formed from the giant impact. Speaking of the giant impact, there were celestial objects, including the dirts, and then they collide each other and grow in size. And after that growth, according to the computer simulation, you can see the collision. The two objects collide with each other, and the debris after that spread out in the space. And then those debris will be collected to form a moon, and that is the result of the giant collision. But what is important is that at the time of the formation, is it made of the Earth itself or the colliding object? We have to understand which one is going to be the reason. By understanding this fact, the colliding object and the Earth, now the ratio of the size of the two objects, and the conditions of rotation, we will be able to have all the detailed information. What is important to understand this is that the giant impact that would take place in the other space-time, we will be able to have a guess. And by doing so, the Earth-like planet, how easy this kind of a planet created. And for this to be studied, first, the colliding object on the Earth, which one is going to be the first? We have to study that. And for that to be achieved, the way we are going to do the study is to compare the elements and the composition of the elements. And what is problematic in this study is that we have the crust under the Earth, and within the crust, the green area, which accounts for 90% of the volume. Most of the majority is considered as mantle, and we were not able to return them from the sample returns from the moon. Therefore, this mantle portion, we have to acquire the rocks that belong to the mantle. And according to the past studies, that it is made up of olivine. It is the rock that contains a large majority of olivine. The ratio of iron and magnesium is also going to be studied. Where we can find this kind of material, the Kaguya, which is the lunar orbital satellite launched by Japan, you can see the red dotted dots. And we have already identified these places contain a lot of olivine. So we are going to select one of those red dots, and which one is more suitable according to the topography. And we did different kinds of analysis, and as a result, we have determined a selected landing point. The area that contains this desired the rock elements is limited, and then the place is also inclined. Therefore, as Dr. Murray explained, the slim pinpointed navigation system, and then it can also land on the inclined slope. That kind of technology is essential for this kind of research. And you can see on the surface of the Earth that this is the place we are going to make it landed. And based on the research data, we have identified this place for landing, which is called Shiori, and around this place we are going to make the lander to land. And we are going to use the spectroscopy, similar to SLIM. We have developed a small-sized camera, and Professor Saiki of Ritsumeikan University is the inventor. So in this way, we have put different technologies into the small-sized camera lens, and the mirror, which is going to be rotated, and so that the scanning will be enable the lander to view the situation on the surface. And inside the instrument, there's going to be a camera to be installed, and then the observation on the surface will be done. And there are going to be 10 waves are going to be monitored and studied in order to do the analysis of different rocks, including olivine. And this is the last photograph. The two project managers are shaking hands. Please look forward to the research results. Thank you very much.
On the moon, exactly at a spot that you desire to land, and by collecting materials from there, the formation of the moon from the giant impact in the past may be elucidated to understand whether the moon is the colliding object or whether the moon was originally part of the Earth. And so you would like to land on a precise location that will enable us to collect a substance that may lead to understanding of that. And last photograph was a handshake between the two project managers, Maejima and Sakai-san, of these two projects. That was a wonderful photograph, symbolic of this project. Thank you very much. Over 90 minutes, we have been live streaming the launch today, and we are coming to the end of the live stream. XRISM X-ray imaging and spectroscopy mission will be observing stars, galaxies, black holes. Large astronomical structures will be observed to understand the formation of these structures. And small lander for investigating moon, SLIM, will attempt a pinpoint landing to understand how moon was formed. Actually, at JAXA ISAS, ahead of XRISM SLIM, there will be a series of projects and missions. For example, I myself am involved in solar observation satellite Solar C with ultraviolet. It will be able to do a very precise observation. We will have a series of these important challenging missions. The outcome of the current missions will lead to the future projects. And please continue to look forward to what we are able to achieve in these future projects. Thank you very much for watching.
The sound suppletion water system has been activated.
22、26、24、25、26、27、28、19、20、21、20、19、18、17、16、15、14、13、12、
Flight mode on.
10、
The flight mode is on.
同様電池起動。
The thermal battery has been activated.
全システム準備完了。
All systems are go.
メインエンジンスタート。
The main engine ignition.
ソル BA 点火。リフト。
Solid boosters ignited. Lift off.
プリズムスリムを搭載した H2A ロケット47号機は2023年9月7日午前8時42分11秒に種子島宇宙センターから打ち上げられました。
We have a liftoff of the H2A launch vehicle number 47 from JAXA Tanegashima Space Center at 8:42 and 11 seconds a.m. on September 7th Japan Standard Time.
打ち上げ以降ロケットの管制は吉信発射管制塔から竹崎総合司令塔に引き継がれています。
Following the liftoff, the operation control of the H2A has been switched from Yoshinobu Blockhouse to Takesaki Range Control Center.
60、
打ち上げ後1分が経過しました。
It's 1 minute into the flight.
ロケットは現在東方向の太平洋上へ飛行しています。
The H2A is now flying about the Pacific Ocean to the east.
燃焼終了。Solid boosters have burned out. SRBA 分離。Solid boosters have been separated.
15、16、17、18、19、120。